Okay, I think I'm recording. All right, so go back to what I just said. We're meeting face to face. We would be having labs where we were taking data, and I would give you a lecture on essentially the material that you see in this packet. This packet really contains the mathematics you need to do lab work. And this is really not a physics lab per se. It's really a science lab. This is a lab that really applies to any of your science courses, or even if you're doing psychology, any kind of an endeavor that is scientific where you collect data. This kind of information is important. So this is really even beyond physics. All right. But as in this class, I try to teach you how to be scientists. And so part of this is understanding what this information means. So in the lab, we're gonna really talk about the mathematics behind really analyzing scientific data. All right. And I'm hoping for a lot of you, this is review. It's covered in a lot of this is covered in your chemistry class. Possibly it even applies probably more to your chemistry than it even does your physics in many ways. But let's just kind of talk about some concepts. All right. So I give a lecture. We're meeting face to face. I give a small lecture on this information. So I'm going to kind of go through that lecture now. All right. So let's talk about some vocabulary. And some of these words are used interchangeably without people thinking about it. But we have a concept called precision and accuracy. So accuracy versus precision. All right. And so I think a lot of people use these words without really thinking about them too much. But when you're taking, when you're measuring something in the laboratory, so let's say you're doing an experiment to try to figure out the gravitational acceleration. You should be talking about chapter 2, chapter 3 about now anyway. But let's just say you're calculating, or you're trying to calculate something where there is a scientifically accepted answer. All right. And so what you'll take data, and essentially the accuracy is how closely your data your measurement matches the correct value. So essentially the accuracy is how close your measurements agree with a scientifically accepted value. That's your accuracy. If I'm trying to measure, the acceleration of gravity, 9.80 meters per second squared. Well, how close did I get? Well, let's say I got 9.75, whatever. How close is that? How accurate is my measurement? If I'm trying to measure the speed of light, how close did I get? All right, so I'm comparing with something that the scientific community has accepted as truth. Then you have precision. Precision is basically refers to how repeatable are your measurements. All right, so it's the precision is it's a measurement of how closely your measurements agree with each other. Now, you can be very precise, but possibly not very accurate. So I always kind of like to draw a little bullseye. So I'm going to kind of erase these words here. And let's kind of write this kind of as a picture, what I'm talking about. So accuracy, if I'm playing darts and my object is to try to get, let's say, the center of the bullseye, well, I would be accurate if this is my bullseye. I'd be accurate if I was getting my darts right along in here. That would be if that's my target. I would consider that an accurate. I would consider that if the target value is the center of the bullseye. I'm just kind of drawing this in a picturesque way, and my data is right around that center. I would consider that accurate data. However, let's say I have a situation like this. Here's my bullseye. And let's say all my measurements are right up along here. I'm hitting this spot. So I'm very precise, but I'm not accurate at all. I mean, the real answer is right here at the center of the bullseye, but I'm really agreeing with myself quite well. That would be considered a very precise experiment. And what this really represents is that there's probably some systematic error that I'm not accounting for, because that error is visiting every single one of my measurements. Or something's wrong with the experiment, or I'm not taking account of something, because I'm doing the same thing repeatedly. But as you can see, I'm consistently off the target quite a bit, and in a regular way. All right, so that's where we talk about precision versus accuracy. All right, and so we'll talk a little bit more about that, as I proceed. But so I'm going to kind of, again, take this into account. Now, one of the things that we also discuss in measurements is what's called uncertainty. All right, so I'm going to leave these two terms. And the question is, and this kind of gets into the significant figures. There's no such thing as a perfect measurement. There's always going to be some uncertainty. All right, so the uncertainty is a quantitative measure of how your measurements deviate from the standard or expected value. All right, so we talk about uncertainty. And essentially, it's a quantitative measurement of or measure, I should say, quantitative measure of how much your measurements deviate from a standard or expected value. So typically, let's say, as an example, we measure some quantity we give by the variable x. We measure x. So we have the various data x, for instance. Now, oftentimes we refer to the uncertainty mathematically. We refer to that as delta x. So it looks like a equilateral triangle. This is the Greek letter. Physicists use, every letter in the alphabet. If you were to ask me a given letter of the alphabet, whether it be capital or small, I could tell you 2 or 3 things that's typically used for in physics. And physicists can't just use the 52 letters, if you will. I mean, 26 capitals and 26 smalls. Physicists have to actually borrow other people's alphabets as well. So we actually borrow the Greek alphabet. All right, and I can pretty much tell you, if I go through the entire Greek alphabet, I can pretty much tell you, what the various Greek letters are used for as well in the typical way. So this is what we call capital D in Greek. It's called delta. All right, small d would be here. This is the small, looks like a little cherry. The triangle is capital D. When the capital or delta is typically used to talk about a difference in something, a difference. And so we'll see kind of how this works out. But uncertainty is oftentimes given as if you're trying to measure something like X, your uncertainty would be called delta X. Or oftentimes you might even call it little delta X. Like you'll see it, what I'm going to probably write out here in these lab measurements, oftentimes it's little delta. Anyway, look at it, use the delta to talk about that. So let me give you an example of an uncertainty calculation. And this is recorded, so if you don't get something, you can always, I'll put this video on YouTube, and you'll be able to watch it at your own, at your own speed if you wish. Again, one of the good things about showing up to something like this is that you get to participate and ask questions. All right, and so again, if you're just waiting for the YouTube video, you don't get the opportunity to ask questions or to say, hey, I'm confused about something. So you don't get the chance to interact with the professor. So again, so keep that in mind. If you say, oh, these things are going to be on YouTube anyway, I'll just wait for the YouTube video. Well, that disallows you from participating. All right. So let me give you an example. Let's type right EX, for example. All right, example. So you might say that the mileage on your car is 45,000 plus or minus 500 miles. Okay, so you might say that. This means that the true mileage you don't really know the true mileage. Let's say they say you're not in your car, you can't just look at the odometer. So it means that the true mileage is a value between 44,500 miles and 45,500 miles. Oops. Right? You don't know, it's some number that's in there. You don't know, but you have a confidence that your uncertainty is only 500 miles. So that's your uncertainty. If I knew exactly what my mileage was, let's say it was spot on 45,000, I would tell you it's 45,000. But the fact is, I'm like, I don't really know. It's I give it an uncertainty of 500 miles. It's either it's somewhere between. Certainly, I have great confidence that it's somewhere between 44,500 and 45,500. Okay, that's my uncertainty. So I would write something like this. I would say that that my mileage is, I'll say L plus or minus little delta L, where L, we'll say, is 45,000 miles. And my uncertainty in what? My uncertainty in my measurement, I'm just calling the mileage L, whatever. And so that's going to equal 500 miles. That's my uncertainty. I'm not sure. So I have confidence that my mileage is definitely, I have very high confidence that my mileage is definitely in that 500 or 1,000 mile range, plus or minus 500. I can also write a percent uncertainty if I wish. So I can say percent uncertainty that would equal the uncertainty divided by the nominal value multiplied by 100%. Right? So in this particular example, I have a limited whiteboard here, so I'm going to erase the verbiage. Let me give you a value here. So percent uncertainty, again, what is it? Percent uncertainty is delta L over L times, and this is going to give you a unitless number, length over length, cancels out, times 100%. All right, so percent uncertainty would equal 500 miles divided by my nominal value, 45,000 miles, and miles over miles cancels out, multiplied by 100%. So 500 miles may seem like a lot of miles, but in reality, when I break it down, it's not much at all. So percent uncertainty, and I actually never computed it. Give me a moment. 500 divided by 45,000 times 100. 1.11%, we'll say. So I could say, for instance, that I know my mileage to plus or minus 1.11%. So I know the mileage of my car within plus or minus 1.11%. I could say that too. So I can literally write the uncertainty as a value in terms of whatever the units I'm talking about, in this case, length or mileage, or I could say that my uncertainty, or I could say I know the mileage of my car. I mean, I can say this English sentence right here. I know the mileage of my car with an uncertainty of plus or minus 1.11%. So again, it makes it look like I know things pretty well. You tell me, if you look and say, well, you don't know your car's miles within 500 miles. Well, given that the nominal value is 45,000 miles, that's not bad. All right, and so 1% is not bad. All right, what happens if I have if I have something that's maybe multi-dimensional, or maybe I have variables, I have a couple of variables multiplying each other? What happens then? All right, let's talk about the uncertainty of an area. Okay, this is just a one-dimensional calculation here, but what happens if I have, many times in science, you have multiple variables that multiply each other? Trouble whiteboard here. All right, so let's take, for instance, we'll say the area of a floor is another example. We're going to do a two-dimensional problem. The area of a floor, or anything really, is calculated by a length times a width. All right, well, the length and width are two separate measurements. Each of which has an uncertainty. All right, so again, I'm going to have a squaring issue here now. I mean, how do I take care of that? So let's just say, for instance, as an example, we know the length. So we know the length is equal to 4 meters plus or minus 2%. Okay, let's say I know that. And I know the width is going to be, we'll say 3 meters plus or minus 1%. And the question is, well, what do I do about the area? Well, one of the things you can do is there's a little shortcut you can do. I mean, I'm going to kind of show you both ways. Again, this is really important, when you have multiple variables. And again, this is true that you can do this if the percentages are not too big. So let's see here. So again, I'm telling you my example. The length of my floor is 4 meters plus or minus 2%. And the width is 3 meters plus or minus 1% in my example. All right. So one of the things you can do, if the percentages are small, we can add them. All right. So what I mean by that is that the area is going to be length times width plus or minus the basically the percent delta L plus the percent delta W. So what is that in numbers? Well, that would be, the area would be 4 meters times 3 meters, 3.00 meters, plus or minus what now? 2% plus 1%. So what I would expect possibly is the area may have 4 times 3 is 12. Let's see, 3 is big, so that. So 12 meters squared plus or minus 3%. Again, I can do that if the percentages are not too big. Now, again, you should not, as a scientist, you should be asking me to prove that. That's kind of an interesting result, but does it really work? Well, let's see. How would I do it if I didn't have the shortcut? What would I do? Well, I would want to figure out the difference between the minimum and the maximum area. So what is my nominal area? Let's figure that out first. So we'll say A nominal. So I'm going to say, well, first of all, A nominal is nothing more than 4. So I'm going to prove that what I just showed you actually is true. Nominal area is going to be length times width. All right. So it's going to be 4.00 meters times 3.00 meters, or 12.0 meters squared. Okay, so that's the nominal, right? What about the minimum? The minimum area would occur if I minimize the length and I minimize the width. So it would be L min times W min. All right, so what would that be? Well, I know that there's an uncertainty in my length of 2%. That means in the smallest possible way, the minimum length would be 98% of the nominal. So I'd have 0.98 times 4.00 meters. And the minimum width, well, I told you also in the given that has an uncertainty of plus or minus 1%. That means the minimum I would expect is 99% of the value. So I'd say it's 0.99 times 3 meters. All right, when I work that out, I find out that A min will actually will equal 11.64 meters squared. All right, so it differs by 12 meters squared. You can see it's smaller. You could also go the same way. This is an extra calculation that we don't actually have to do, but I'll show you this anyway. is you look at A max. If you want to find the maximum value something can take on, well, you maximize each of the variables that goes into it. L max times W max. Again, this is a calculation we don't have to do. I'll show you in a moment, but I'm doing it anyway, just for edification purposes. So given that the L max, given that the length has an uncertainty of 2%, that means I could go over by 2% or 102% the value. So I can write this as 1.02 times 4 meters. And then I max out the width, and again, I told you that's has an uncertainty of 1%, or I can go over by 1%, or I can 101% the value, or 1.01 times 3 meters. When I do that, I find out that the maximum area, A max, would then be 12.36 meters squared. Let's take a look at what our delta is. Notice that minimum is 0.36 meters squared below 12, below the nominal, and maximum is 0.36 meters squared above the nominal. So anyway you look at it, my delta area is going to be, I'll just pick one, 12.36 meters squared minus 12 meters squared, or 0.36 meters squared. That's my uncertainty. What's the percent uncertainty? Percent uncertainty. That's going to be delta A over the A nominal, or 0.3, and then multiply by 100%, of course. That'll be 0.36 meters squared divided by 12 meters squared multiplied by 100. And it turns out if I do that calculation, I find out that the percent uncertainty is 3%. So yes, that particular shortcut works just fine. But you should not believe me. Again, in science, you don't believe anything unless you prove it. You know, science is all about proving things. So I tell you something, you ought to say, prove it. Right? So the onus is upon the scientist to prove everything, because the scientific theory is based upon a fabric of proofs and logic. And that's true for physics, chemistry, you name it. Okay, now we talked about accuracy, we talked about precision, we talked about uncertainty. Now, the concept of precision leads us into the significant figures discussion. Any questions so far from anybody? Okay.
I have a question.
Yes.
For the A minimum equals length minimums, minimum, W minimum.
Yes.
Can you re-explain the 0.98% when it comes to minimum?
Yeah, so I
0.98 times 4, and then
right. So I told you that the length has an uncertainty of 2%, and the width has an uncertainty of 1%. Right. That means whatever the length is, I say 4 meters. I don't really know that exactly. It's 4 meters plus or minus 2%. So that means that I have to ask the question, well, how small can it be, or how large can it be? Again, 4 meters is nominal. I could be 2% smaller or 2% larger. If I'm 2% smaller, then that really means that 100% minus 2% are 98%. That means that my length is really 98% the nominal value. How big can it be? Well, it could be 2% bigger. It could be 2% larger than nominal. That means that my nominal length is really 2% more, or 102%. Right. So again, the 98%, it just tells you that I could be as small as 98% of the values. I'm really confident that my length is 4 meters plus or minus 2%. Whatever the actual value is, I have great confidence that it's somewhere in that 2% range. So it could be smaller than 4, i.e. it could be 98% that nominal value. And again, for width, well, what's that going to be? Well, it's plus or minus 1%. That means the smallest the width can be is 99, or it's 1% less, or 99% the value. And the largest it could be is 1% more, 101% the value. Does that make sense?
Yes, it does. Thank you.
You betcha. Any other questions? So again, this lecture here is a physics lecture, a chemistry lecture, a biology lecture, all in one, right? This is you can call this a science lecture. So this is anything you can where you take data, this lecture applies. All right. Let's move on to significant figures. So if we're meeting face to face, the very first thing we would actually do is we do a relatively simple lab. What we would do is we would be measuring densities. So if we're meeting face to face, so a face to face lab, we didn't have COVID. We would calculate densities of various objects made of different materials. We'll be told what the materials are. So I would tell you, so one of the objects is a spherical metallic sphere. One of the and it's made out, I don't know, maybe we'll say nickel or something, whatever I would tell you what it's made out of. Another object is a cubical object. And I think another one's like a rectangle or something. All right, and so we would do what? Well, we want to find out the density, and then what would that be? That would be the mass divided by the volume. All right. Well, each one of these objects has a different way of calculating the volume. Right? As you go, you figure out the sphere. You need to know the radius. The volume would be what? 4/3 pi r cubed. For the cube, it would have, each side would be s. The volume would just be s cubed. And for the rectangle or the cuboid, we'd have, a length, a width, and say a height. The volume would just be length, width, height. And we go on a mass meter, and we'd figure out, electronic mass meter, you'd figure out what the mass is. And the mass meter, you would know what the uncertainty of the mass meter is, and then we would measure the lengths of these various things with different measuring devices. So you'd have the crudest one, it'd be a ruler. You only know a ruler as good as the smallest increment on a ruler is a millimeter. So you can't do any better than 0.1 centimeters if you're using a ruler. You don't know, there's no way that you know that value any more precisely than that. Okay, that's called, so in the language of science, we call that the least count. The least count is the smallest increment on a measuring device. Called the least count. Now, so what you do is you would calculate these various lengths. What do you need to know? Well, you need to know, if you're really doing precise, you would actually want to probably consider this a length, width, height. Even though this cube is all the same, you can't believe that. You really need to make sure that you measure all three of these dimensions separately and prove to yourself that they're all the same, right? And you do all this, and you figure out, you'd basically be multiplying, okay, r cubed. Well, there's a uncertainty in the radius. So if you're cubing it, you have uncertainty plus uncertainty plus uncertainty. There's going to be, the uncertainties are going to have an additive effect. And again, it's a three-dimensional physics, so you're going to have an additive effect here and here. Those will be uncertainty in length, width, and height. And so what you end up finding out in this class is you'll end up calculating different densities. And you'd have to compute, and you say, okay, well, what is this? Oh, it's made out of nickel. You go to your iPhone or you go to your book and figure out what the scientifically accepted value of the density of nickel is, or the density of whatever the other things are, steel and something else. I forget what the other ones are. You do that, and so you have one set of values, let's say, for using the ruler. But then you'll use a caliper. A caliper is a much more accurate, much more precise instrument. You can get, a lot better length measurements from a caliper, and then you go even more precise, and you use what's called a micrometer. Okay, so you'll actually use 3 different measuring instruments in this lab. Each one of them has its own uncertainty. The ruler being the crudest, the caliper being in the middle, and the micrometer, micro meaning a millionth of a meter, micrometer being the best. And then you'll get various densities, and so the idea is, you can, depending upon what tool you're using, that determines how well you know something. So for instance, if I'm using a ruler, the least count on a ruler is going to be the millimeter. So for instance, if I'm taking a measurement with a ruler, a length measurement using a ruler is good to plus or minus a millimeter, or plus or minus 0.1 centimeters. So if I'm measuring something in centimeters, a good measurement might be length is 23.7 centimeters. Now, maybe I can estimate and say 23.71 centimeters. But if I were to do something like this, 23.716429 or something like that, that's garbage. There's no way using a ruler that I could know this length that well. There is no way. I'm stretching it. This is my first value of uncertainty. I'm kind of eyeballing to get that 1. All right, but there's no way that I can argue 6429. No way. I can't have that many what we call significant digits. My measurement device is not that good to do that. I cannot argue that kind of precision. And you'd be irresponsible as a scientist to do that, because the scientific community, if they see you publish something and you have a value like that, they're going to believe you. They're going to take that as a fact. They're going to say, well, we're going to use this as a value that we really know and use that in our experiments. Well, no, and so that would be irresponsible to do that. The responsible scientist would publish something like this, or maybe really something like this, and explain, well, my 1's kind of like, I think it's that 1. I have uncertainty. All right. Now, I could go even further and say, well, I could go, for instance, to a caliper and see that I even have more digits. So what this gets into the concept of significant figures. All right. And so it's very important when you're making measurements, particularly when you're multiplying values together, adding values, to keep track of how precise each of your measurements is. And so there's rules for that. So if I were to say that I'm measuring something to 36.7 centimeters, for instance, well, the rules for significant figures is, if you write down a non-zero digit, you count it. All right, so all non-zero digits are significant. All right. So I would look at that and say, okay, well, what do I have? 1, 2, 3. So this would be 3 sig figs, as we call it. The non-zero is called significant. That means that I've done a measurement and I can argue through, how good my measuring device is, how precise this value is. And I would write it down and say this would be 3 sig figs. All right. So again, the rules for significant figures are pretty simple in this manner if you don't have zeros. Now, if you have zeros, there's a few other rules you have to look at. Okay, so again, there's non-zero digits, you just count them. 1, 2, 3. Okay, so in this case, 3 sig figs. But what about zeros? Again, if you want to be more clear on this, I did give you a significant figures handout on Blackboard, and it covers probably even better than how I'm covering it. All right. So let's talk about zeros. What happens if you have zeros? Okay, I talked about non-zero values, so that's easy. So zeros are significant except when they serve as only as placekeepers. All right, and so what I mean by that is if I take 0.053, well, this 0 right here, all it does is just moves the first non-zero decimal to its appropriate location. This is really a placekeeper. This really is not significant. It just moves it to the appropriate level of where the number is, where its magnitude is. For me to know this for sure. So again, the answer there would be I have 2 sig figs on this one. If you're not sure, this is a little confusing, you write it in scientific notation. Again, I hope you guys are familiar with that. So scientific notation means, well, what I have is a number smaller than 1, so I go 1, 2. I take I count how many, how far I'd have to move the decimal to get a non-zero digit, and then go after the first non-zero digit, and I would write this as 5.3 times 10 to the negative 2. Now, when you write it in scientific notation, it really does look like, yeah, that's 2 sig figs. If you're confused about it being written in regular ordinary notation, writing in scientific notation clears it up pretty well, that there are 2 sig figs. So the only purpose of the 0 is to move the non-zero digit to the appropriate place. So it's called a placekeeper. It just puts it in an appropriate place. Not significant. Okay. Now, on the other hand, is this clear? But sometimes zeros are significant. All right. So if it's not a placekeeper, so let's say, for instance, I instead have the number 10.053. That 0 is significant. In fact, all of these are significant. If I were to count, it'd be 1, 2, 3, 4, 5. And if I don't believe it, well, I write in scientific notation. Again, I wrote this 3 and this 5 down because I certainly have great confidence that those values are what they are. So in scientific notation, what do I have? I have a number bigger than 1, right? So I move my decimal. Again, I'm going to kind of go, when I first talk about mathematical concept, you'll see that I'll go over it very slowly at first, just to make sure that everybody's on the same page. So when you go and look at my lectures, when we first talk about a sine or a cosine, some of you guys know what sines and cosines and tangents are like the back of your hand. You had it just maybe last year in high school. Some people may have not seen it for 10 years. So again, you know, so if this seems a little slow to you, I apologize, but possibly somebody in the class it's not. All right. So anyway, I move it over one. So what do I get? I'd have 1.0053 times 10 to the first. Writing in scientific notation, it becomes very clear to me that all of these values are significant, including the zeros. 1, 2, 3, 4, 5. So if the zeros, in this case, the zero is not a placeholder. So I'd count it. All right. So is that clear? Now we get to a situation where, let's say I give you another example with zeros. Let's say I give you 1,300. And let me ask, how many significant figures do you think are here? If anybody hazards a guess? It's kind of a trick question. The answer is, it depends. Depends on my precision. What do I mean by this? It could be 2, 3, or 4. It depends. I mean, is this 1,300? You know, is this 1,300 something I'm definitely arguing about, or is it just it's about 1,300? You know, plus or minus 100. I don't know. So for instance, it definitely is at least 2. So I don't know. I have to give you more information on some number like this. How, if you want to guarantee that the number is truly has 4 significant figures, what you do is write it like this: 1,300 and put a dot, put a decimal right there. If I do it that way, the answer is absolutely 4 sig figs. So I can clear this up by putting a little decimal. Don't put a 0 here. You put a 0 there, that's going to count as another sig fig. That's going to count like, oh, that's more precision. That would be 5 sig figs. So don't put a 0 here. You just put a decimal there. And that tells the reader, oh, okay, that value is being argued to be 4 significant figures. These zeros are significant. It's not like, well, I think it's about 1,300. Well, in that case, maybe you're at the best you're talking about is 2 sig figs. But if I see this dot, if I see this decimal, definitely you're talking about 4 sig figs. Okay, so zeros are kind of weird when it comes to significant figures. So again, this is a lecture that would apply to your chemistry class. In fact, those of you taking chemistry, chemists are way more tight about sig figs than physicists are. I mean, I've had chemistry classes in my past when I was an undergrad where you were graded on your precision. You know, we do a chemical titration, and you wanted to really be accurate. I mean, really be precise on that. You know, and I had a lab partner. She actually left lab twice crying because I was such a pain. You know, because I want to do this titrations extremely, precisely, and it drove her crazy. You know, but anyway, but yeah, we had some of the best results in class, and because your grade depended upon, how close. How close you can predict, like, okay, what chemical is this? I don't know what it is, but let's see if I can do a titration to figure out what it is, right? And so so our student T confidence and everything else was very precise because we did we did that kind of a level of precise experiment. All right. So again, sig figs are you'll get hit over the head with sig figs in chemistry. Much more so. You're not going to get that from me, particularly if we're doing physical measurements in this class, because our materials and our labs are not very good. I mean, if you're at NIST or MIT or someplace like that, then you'd have some really high caliber instruments. TCC, you're not going to see that kind of caliber instruments. So I'm usually good within plus or minus 5% usually when in the quality of the instruments that we have. All right. So again, in chemistry, you can control things much better with chemicals. Okay, let me give you some examples to see if you can kind of, see if you can tell me how many sig figs. So let me ask you 0.0009. How many sig figs is that? Anybody? You guys with me?
One.
Huh?
It's one.
One it is. Yes. One sig fig. Very good. And why you say that is these zeros are nothing but placeholders. If you're confused, you can just write this. 9 times 10 to the 1, 1, 2, 3, 4. Oops, 10 to the negative 4. Right in scientific notation. When you do that, yeah, you can definitely see it. One sig fig. Let me ask you this: 15,450.0. How many sig figs there?
5.
What was that? What was that? What was your answer?
Said 5.
Actually, it's 6.
5. Sorry about that.
It's 6 because it'd be 5 if I didn't put the 0. But this 0 here, when it's after the decimal like this means that I'm arguing that that 0 should be there. That's actually, see, zeros are weird. When you put a 0 like this, now it would be 5 if I did this, but that would be 5. But given that I wrote this 0, that means that I'm telling you that I believe that 0 is there. I believe in my experiment. I have great confidence that that value is 0. So this would then be 1, 2, 3, 4, 5, 6. Zeros are tricky. Let's see here. How about 87.990? How many is that? Anybody?
Would it be 5? Would it be 5 now?
Yep. Because I can argue that 0. It's not a placeholder. Absolutely right. 5. Indeed. Not a placeholder. And how about here? 30.42.
4.
Yes, 4. Now I want to look into lab real quick, and I saw an example there that I want to point out. All right, I'll get back to it. I'm still talking about my notes here, but I'll go into the lab theory next. All right, so let me next talk about adding and subtracting numbers with sig figs. All right, so again, that's very important. So oftentimes, well, you're going to have a value, you're going to have something you measure, it's going to have so many sig figs. But then, when you're doing a physics experiment or a science experiment, chemistry, whatever, it doesn't really matter, something science, you're going to have to, oftentimes your values are going to be added together or multiplied together. In fact, that happens almost all the time. So let me give you an example of addition and subtraction. So I'll give you an example here. So suppose, so pay attention here. Suppose that you buy 7.56 kilograms of potatoes. In a grocery store. As measured with the scale of with precision 0.01 kilograms. Okay, so again, how do you know that? Because I'm saying 7.56. I have a value I have a non-zero value. I have some value that I'm arguing that is in the hundredths place, the TH, hundredths. All right. So again, I bought that in a store. That's how good the store at Tom Thumb is, or the scale Tom Thumb. All right. Then you drop off 6.052 kilograms of potatoes in your laboratory. As measured by a scale with a precision of 0.001 kilograms. Finally, you go home and add 13.7 kilograms of potatoes as measured by the bathroom scale with a precision of just 0.1 kilograms. So finally, you go home and add 13.7 kilograms. Of potatoes as measured by your bathroom scale. With a precision of 0.1 kilograms. So the question is, what is your mass of potatoes now? All right, so again, you went to the grocery store, you added 7.56 kilograms of potatoes, and that was measured by a scale that at the store that's accurate within 2 decimal places, is 0.01 kilograms. You go to your laboratory where you have a much more precise lab or scale, and you drop off 6.052 kilograms of potatoes. That's measured by a much more precise 0.001 kilogram scale, or basically down to a gram. Finally, you go home and you use your crude bathroom scale. You add some potatoes on it, and you find out that you've added 13.7 kilograms as measured by the crudest scale on your bathroom, 0.1 kilograms. The question is, what is your final answer? All right, so let's write this in terms of mathematics. So again, you have 3 different so you have additions and subtractions, but all 3 of your values have a different precision. So how do you do this? Well, start out by saying, okay, you have 7.56. So let's be careful with our arithmetic here. That's where I'm starting off. I'm at Tom Thumb or Kroger's, whatever, and I have potatoes that I bought, and I've measured down to the 2nd decimal place. I go to my lab and I say, well, I'm going to take away 6.052. That's a subtraction. Then I go back home on my bathroom scale, and I'll add 13.7 kilograms. And that's a plus. Okay. Line up all your digits appropriately. When you do that on your calculator, you'll get what? Your calculator is going to tell you, well, the answer is 15.208 kilograms. But is that really your answer? The answer is, Now, that is what your calculator tells you. This is your calculator. But that's not what you should write on your paper. You know, so essentially, you are limited, or your calculation, your measurement is limited by the worst precision measurement that in your calculation. So the bathroom scale measurement ruined it for everything else. Or in this case, your 0.1 kilogram measurement. So yeah, you did a beautiful job in the laboratory, and the Kroger had a precise instrument, but the fact is you messed everything up by using this crude instrument. So you can't argue a number this good. The best you can argue is to go 1 decimal past. You can say, okay, I want to go 1 decimal past. Let me go take the next digit. Is that 5 or greater? No, it's not. So I keep this decimal same. If it's 5 or greater, I make that a 3, right? So my real answer is really going to be 15.2 kilograms. I cannot argue any better. The total precision of this additions and subtractions is no better than the worst precision of any of my measurements. In this case, my worst precision is the potatoes on the bathroom scale. So it basically made my entire addition and subtraction measurement only as good as that. Doesn't matter I use a very precise laboratory instrument. Fact is, I use a crude instrument, and so my answer is as crude as that crude instrument. Okay? Any question about that? Let's look at multiplication real quick. Multiplication and division. Little somewhat the same, but but let's take a look at it. So let me I'm going to erase this. That's addition. So what I just got done was addition and subtraction. But of course, we have multiplication and division as well, right? So let's give you an example here. I want to find the area of some sort of a, let's say I have a circular object with radius r 1.2 meters. Okay, that's my object. Again, another example. I'm gonna do multiplication and division now. Let's do multiplication. I'm gonna find the area. So it's the area of a circle, pi r squared, right? So now I might know pi really well. So for instance, I might do this calculation. I go to my calculator and I know pi really well. I could write this as 3.1415927, for instance. All right, I can know pi to 1, 2, 3, 4, 5, 6, 7, 8 decimal places, 8 significant figures. All of those are significant. But I'm multiplying it by a number that only has 2 significant figures. I mean, maybe I measured this with some sort of a crude device. So I go to my calculator. What's my calculator tell me? Well, my calculator is going to give me some stuff like 4.52 38934. That's my calculator. But let me ask you, what should my answer actually be? I'm limited by, I should tell you this, I'm limited by the least precise value. So again,
4.5.
4.5, absolutely right. The least precise value has only 2 sig figs. That means my answer has only 2 sig figs. So again, multiplication and division is limited by the value or contribution, whatever you want to call it, with the worst precision. So yeah, so now it's interesting. If you're to, I do a lot of programming, so I done a lot of writing and physics software in my career, and oftentimes you'll look at the their file that has all the constants in it, and they'll usually have pi out to, like, I don't know, 20 or 30 decimals. And I remember when I was younger and not as wise, I went to my boss and I said, "That's ridiculous. Why would you need to know? Why would you need to write out pi that way?" And he looked at me seriously and he says, "Well, why would you want to artificially put a lack of precision in your calculation? Because we're going to have lack of precision anyway. Why would you want to have it in? Why would you want to enter? Why would you want to enter it in as pi?" And I'm like, "Okay, sorry." So, but anyway, I looked at that code and I thought it was kind of funny that they were writing pi out to that many decimal places, right? But the reality is, why artificially insert error in your calculation? We don't need to, right? All right. So now what I'm going to do, those are my lecture notes. I'm going to go into the lab now and talk about that. And a lot of this I've talked about already, but again, I talked about sig figs. I have one other thing I'm going to talk about with sig figs, or some brief thing, but we'll get to it. So in the lab, now the way this lab's written out, and this is the way labs used to be written when we met face to face. You always have a pre-lab, and then you have a theory, you have the experiment, and then you have a post-lab. That's generally what how labs were written. Most people who wrote the labs, I think it was Professor Ray Benj wrote most of our face-to-face labs, and I believe Professor Dr. Edmonds wrote a lot of some of those labs, and he's pretty much wrote, I think, most of the simulation labs that we use now with COVID. But again, that's the way kind of things used to be. So somebody mentioned, well, I'm a little confused. What do I actually answer? Well, the reality is, if you look at this lab very carefully, if you see something that's a question, or you see something that's a blank needs to be filled in, then you need to answer it. So if you look at this beginning here, analyzing pre-lab, you'll see the first 6 questions. The first 6 questions are to be answered. So, number 1 is answer some sig fig questions. Number 2, and I'm going to talk about this. You're going to talk about average to standard deviation. I'll talk about that in a minute. The third one, we're going to talk about percent error. And so I'll mention about percent error. And again, this is something I'm going to talk about. The fourth one, we're going to talk about what are the axes of a graph. So again, we'll mention this. It's voltage. So it's basically current versus or voltage versus current. What does that mean? How do you write that down? Again, I'll talk about that lingo in a moment. The fifth problem is really calculating the standard deviation of a set of values. I'll go through that for those who haven't seen that. And then again, number 6, I talked about number 6 already. What's the difference between precision and measurement? Precision and accuracy. And again, I talked about that already, right? So I kind of gave you the answer number 6. So again, these are going to be things I'm about to talk about. I mean, I've already talked about number 1. I'm on the first page of the theory. I've talked about significant figures. So I'm on, I'm going on to, I guess, I don't know if you have the lab with you. There's the top page, page 1. These pages are not numbered, unfortunately. Second page. I'm on the third page. The third page, the first word says, first words on that are final digit. So if you look at that, you'll see a little table, and you'll see a calculation for sigma. So again, I've talked about significant figures. So I'm not really going to go into that per se. Now, well, actually, here's a good example here. So on the third page of this lab, in the theory section, they give me an example of, well, what would you do here to calculate significant figures? So they say, okay, well, you have, let's say you're taking a physics 2 class and you're measuring voltages. All right, and so you see that you have a little table. And you say, okay, well, I have a table here, 12.334 volts is a value, 12.412 volts. I'm trying to measure something, and I'm getting values that differ from each other. Another measurement, I get 12.377 volts. Another measurement is 12.531 volts. I measure this thing again, I get 12.402 volts. And I measure another time, I get 12.40450. I think I got these right. So again, I'm trying to measure the same thing. And again, it's what's called the potential difference. We talked about that in physics too, but it doesn't really matter. These are just values. These could be kilograms for all we care. It doesn't really matter. But anyway, 12.334, 12.412, 12.377, 12.531, 12.402, and 12.450. So you look at it and say, okay, well, definitely I always see 12 point, right? But where I start seeing things vary is on this next digit, the 3. Here it's a 3, 4, 3, 5. I mean, that's where I'm starting to see variation. That's where I'm having my first, how does he put it? Measure of uncertainty. This is my first uncertain value. So the 10th place value is the first digit of uncertainty. Now, it's kind of like if you're taking a measurement and maybe the 12 is solid, but you have, the next digit's kind of flicking around 3, 4, 5. It's trying to settle on something. It's not quite settling. Well, that digit's uncertain. And you can clearly see, I don't know what this answer. So how would I figure it out? Well, one of the things you can do is if you take multiple measurements of something, well, you have data, multiple measurements of something. So when you see, let's say a large amount of data or even a small amount of data in this case, one of the tools you have at your disposal is statistics. Statistics is a very important branch of mathematics. And anytime you want to try to get an answer when you have uncertain data or maybe a large amount of data is to employ statistics. So statistics is employed in physics very heavily. Chemistry, you'll do confidence intervals and things like that in your analytical chemistry class. It's employed anytime you're making a measurement in science. You want to try to employ it to within, say, 5 or 6 what are called sigmas. When they're doing the Large Hadron Collider, when they're trying to find the Higgs boson or Higgs particle in the Large Hadron Collider, they only could conclude that the Higgs boson was discovered given that their data was within 6 sigmas or standard deviations of precision. When they had that kind of precision, that's when they knew that they can say, yea, verily, a Higgs particle does exist, but only until you have that kind of precision, right? And so again, and of course, in psychology, even in the business world, statistics plays an important role. So what do you do here? Well, first of all, you want to do is you want to calculate a mean. Now, again, so for some of you, this might be very boring. For others, maybe you're not as keen on this. So again, I'm teaching to the common denominator. So what I want to do is I'm going to get a nominal value. Why calculate the mean? So let's just say, I don't know, I'm going to call this let's just say this variable that I'm calculating is on, I don't know, I'll call it A. So I'm trying to measure what I'm calling A, or call it X, I don't know, whatever. Doesn't really matter. All right, so this might be X1, X2, X3, X4, X5, X6. All right, and so, or I can say that in general, a value is given as what's called X sub I. So I might say that in a particular value, I might refer to it as X with a little subscript I being an index that in this case is 1, 2, 3, 4, 5, 6. I would refer to this as X sub I. Right, and so an I is just an index counter. It can take on the values in this case 1, 2, 3, 4, 5, 6. It just is in this case a label. All right, and so mathematically, if I want to calculate the mean oftentimes you give an overbar to it. So I want the mean value. So I call it the mean. So the variable I care about is X. The mean, I call it X overbar. So again, this is something that I'm hoping all of you know, but I would add up all the values, X1 plus X2 plus X3 plus X4 plus X5 plus X6 in this case, and I would divide by how many values there are, 6. So again, if I gave you guys an exam and I want to find the average score, I'd add up all your exam scores, divide by, I think I have 22 of you now. Divide by 22, I get an average, right? So again, but how would you say this in more advanced mathematical nomenclature? Well, you'd say that the mean would be the summation over I, or maybe going from 1 to 6 of X sub I, and I would divide by what? We'll say I equals 1 to N, capital N. I would divide by capital N. That's my mean. In this case, capital N is equal to 6. So this is a fancy way of saying, now this is the summation. This is another Greek letter. This is your Greek letter sigma. So we're borrowing from Greek again. This is capital sigma, and this is little sigma. All right, and so that's your sigma. So we use the sigma, known as sigma. The S is a Greek. This is a Greek S. So S for sum, right? We use sigma, right? So we use this notation in mathematics saying that we're literally taking we're giving the index numbers, incremental numbers going from 1 to N, N being 6. And we're adding all these numbers up, adding them all up, and we're dividing by the total number that there are. We call that the mean. All right, and so if you were to calculate the mean of all of these values, you'd find out that you'd get about 12.4 volts. I mean, if you were to add it all up, you'd have 12.4 blah blah. You'd have something else. However, again, the best you can argue, your first digit of uncertainty is in the tenths place. You cannot argue anything better than that. So again, let me compute this mean real quick. Dr. Edmonds gives it to us. Let me just kind of add it up myself and give you a value. So what's your calculator going to tell you? Well, if I add up all of these values, and I haven't done this, so 12.334 plus 12.412 plus 12.377 plus 12.531 plus 12.402 plus 12.450 divide by 6, I get something like 12.4. So my calculator is going to tell me this. It's going to say this, oh, that's 12.4 417 and a bunch of sixes. 1, 2, 3, 4 6s and a 7. That's what my calculator is going to say. But if I look at the data, I know that the first digit of uncertainty is in the tenths place. Tenths with a TH. So that's as good as my data is. I am not solid until one decimal after the one place after the decimal. I already have I have uncertainty. That means my data is no better than that. That means I truncate right here. So my actual mean is going to be nothing better. And again, this value is 1. It's not greater than or equal to 5. So I can't promote the 4. So my data is as good as 12.4 volts. I can't say anything better than that. My average value is 12.4 volts. Now, I could get a pretty good idea of how uncertain my data is. I can tell you, well, you know, it's in that tenths place. But that's not very mathematical. I want to do a better job. I use statistics. And in a very popular way of doing statistics or measuring uncertainty is using what's called a standard deviation. All right. And so again, what I have out of this data is X bar is 12.4 volts. Let me kind of write that down. And now I want to try to find out how precise is my data. All right. So I just got done computing that X bar is 12.4 volts. Okay, if I want to figure out, so I mean, an average doesn't mean much. Okay, let's say, for instance, I decide I want to take the average of all the homes in my neighborhood, and let's say one of the buildings in my neighborhood is Sears Tower. Well, if I add up, you know, the heights of house 1, building 1, building 2, building 3, building 4, and then I add up Sears Tower, what I'm going to get is really a kind of a garbage answer. I'm going to get an answer that there's a very large height of the average house. The Sears Tower is going to completely mess everything up. I mean, the value, that average is what it is. I mean, I add up all the heights of the various buildings and divide by how many buildings there are, but I'm going to find a value that's quite a bit higher than most of the homes in the neighborhood. So the average is not going to mean much. And how do we know that? Well, we calculate the standard deviation. All right. So standard deviation is going to look kind of like a funny looking formula, but again, we use little sigma for, you know, we call it the standard deviation. Okay, so hopefully a lot of you guys have seen this. It's given by little sigma is equal to, now, interestingly enough, I mean, if I have n values, I actually divide by n minus 1. I'll talk about that in a minute, why I do that. So I divide by, I have 1 over n minus 1. What I'm going to do is I'm going to add up all the deviations. I'm going to go from I to n. Now I'm going to add up the x sub I minus the x bar quantity squared. And I add this all up. I'm going to take the whole answer and take the square root of it. So again, if I'm adding up the values squared, I don't actually have volts. I have volts squared. So this whole thing inside the square root is going to be volts squared. How I get it back to volts is I take the square root to get it back to the units of volts. All right, so that's now if you take statistics, depending upon what kind of a purist you are, if you have a large data set, generally speaking, statistics really originated in trying to say something about large populations of data. If you have a large data set, you would divide by n, not n minus 1. N minus 1 was discovered when when people like student, for instance, started studying small data sets, and other statisticians at the time, student lived around, and you hear about student's tea. Student lived around the 1800s. Student was kind of laughed at first for doing this. They're like, no. Statistics is about large populations. Why would you want to do statistics for smaller populations? Well, if you're doing a smaller population, let's say six values, you actually use 1 over n minus 1, the way it works out in the mathematics. All right. So and so in our case, even if we're doing 100 data sets, whatever, or 100 measurements, we're still small. We're not 10 to the 6th or something like that, right? No, we're still relatively small. So how do you do this? How do you do this formula? And what is this deviation? Well, this x sub I minus x bar, I already figured out x bar. What I want to do is figure out for each data point, how far away is it from the average? That's called a deviation. I'm going to add up all the square deviations. I'm going to add up all the distances from the average for all the data points, add all that up, I get a sum, and then I divide by, what am I going to divide by? Well, I'm going to divide by 5, right? 6 minus 1. I get some value, and then I take that value that I get in my calculator, and I take the square root of all that, and I get the standard deviation. It really is a measure of how my data deviates from the mean. And that tells you, if that number is small, that tells you that your value is precise. That means that gives you basically a measure of your precision. The value is small, that means that your data, like in the case, if I didn't have Sears Tower in my neighborhood, if I was just adding up all the heights of the houses, you would find a standard deviation that'd be pretty small, which would say that, okay, the neighborhood has roughly about the same heights on the other houses. If I stick in Sears Tower, I'm going to find out that my standard deviation is going to be large, which tells me, oh, okay, there's some massive variability in that data somewhere. Maybe there's what's called an outlier, like Sears Tower, right? And so I would see that in this measurement. So let's kind of run through this, all right? So I'm going to so again, I apologize if I bore some of you guys, but I want to make sure you understand this. This is going to be something that's going to be important for all your classes. Let's kind of imagine we calculate these deviations, all right? So bear with me. If I take x1 minus x bar, all right? Again, I'm going to kind of go through the inside out the deviation formula. That's going to be 12.334 minus 12.4, all right? So if I do that, and if I'm going to want to square it. I'm just going to square it right off the bat. I take this value and I square it. And what do I get? Again, so bear with me. It's going to take about 5 minutes, whatever. It's going to be a little boring, but 12.334 minus 12.4. I square that value. I'm going to get 4.356 10 to the -3. Okay. All right. If I take x2 minus x bar, square it again. I'm taking the squares of the deviations. Take that data point, 12.412 minus the average is common to all the data. All right. So again, 12.412 minus 12.4. I get 0.012. I can just look at this off. All right. So there you go. X3 minus x bar squared. Okay, going to the next data, 12.377 minus 12.4. Square that. So again, 12.377 minus 12.4. And that's going to give me a nice, actually, you know what? I made a mistake here. 0.012 squared. I got to square it. Sorry about that. 1.44 10 to the -4. These are square deviations. All right. 12.377 minus 12.4 squared, 5.29 10 to the -4. Three more. Let's see here. I'm having trouble fitting them in. All right, let's write them. Fit them in up here, I guess. Let's see here. X4 minus X bar squared. I'm just gonna do the calculations on my calculator and write the numbers down because for space. So I'll be doing 12.531 minus 12.4 squared. Okay, that's going to be 0.017161. Okay, I'll do X bar, X5 minus X bar squared. Okay, that'll give me let's see here, 12.402 minus 12.4 squared, 4 times 10 negative 6. And finally, apologize for all this, X6 minus X bar. Again, I'm just kind of going through the painful calculation, but Excel can do this for you as well. 12.45 minus 12.4, square that, 2.5 10 negative 3. All right, so what I want to do now, you go back to that formula, I want to add up all these deviations, all these square deviations. That's the next thing in the formula I'm going to do. I'm going to add up the summation of all the square deviations. So I hope someone's doing this calculation with me so I don't screw this up. I get 4.356 10 to the negative 4 plus 1.44 10 to the negative 4 plus 5.29 10 to the negative 4 plus, let's see, 0.017161 plus 4 10 to the negative 6 plus, last one, 2.5 10 to the negative 3. Okay, I add up all the square deviations. Now I'm going to erase these values here. I add them all up. Let's hope I didn't fat finger something. Add them all up. And this is what I'm doing right now. I'm adding up summation from I equals 1 to 6 of the X sub I minus X bar squared. If I do that, I get 0.02007736. Well, what's the formula telling me to do now? Well, I'm going to divide by 1 over n minus 1. All right. That means I want to divide this value by 5, or 6 minus 1, which is 5. I divide by 5. In the formula, I get 4.15472. Ten to the negative 3. And the last thing I want to do is I want to take the square root of it all. That gives me sig. So take the square root of that. So the square root of 4.15472 times 10 to the negative 3 is going to give me about 0.064457. Blah, 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 what my calculator tells me. Now, again, I have a value that I have to remind myself that this is a measure now that's in volts. So my standard deviation is in volts. Now the question is, well, how well do I know this calculation? Well, this calculation is telling me that the best I can do is really some form of, and basically my precision is right after 1 in the tenths place, right? So this is the hundreds place. So what I really, the best I can really do is I can write down that that the value is only going to be good to what? In the tenths place. So I need to say, okay, well, I take a look at the 6. The 6 is a number that's greater than 5. And so what I really have is that in the limitations of my measurements, my sigma is only going to be good to 0.1 volts. Because I have to take this value, the standard deviation, which is pretty good, but I need to essentially round it such that it is in adherence to the limitations of my calculation, which we have already said is that my first digit of uncertainty is the digit, it's in the 10th place. So I go through all of this. Again, I really want to kind of go through the whole calculation. You can actually go into your Excel spreadsheet, lay all your data down, and I think it's STDEV or something like that in Excel. So I think for instance, if I were to, well, first of all, what's my answer? My answer is going to be that my data is generally good to, well, generally speaking, your deviation can go either way. So actually, I kind of misspoke. I apologize. My deviation, what I really want to do is I want to express my value as X bar plus or minus 2 sigma. So remember, my deviation can be to the positive or the negative. So again, so essentially my deviation is you generally write 2 sigma. So what would I do? Well, 2 sigma is 2 times this number I calculated, 0.064457. All right, and so what I would actually write, so that 2 sigma, if I do this, I get what? 0.064457 multiplied by 2, and I get 0.1289. 14 according to my calculator. Now again, I only know the values as good as the first decimal place. So I take a look and I look, okay, I have a 1 there. Is that 2? Is that greater than 5? No. So what I really have is 2 sigma is really no better than 0.1. So I would actually write that X is really going to be X bar, which is going to be 12.4 volts plus or minus 0.1 volts. All right. So again, sigma is the standard deviation. My uncertainty is always basically given by 2 sigma. So again, I went through the whole calculation and figured out sigma to a nth degree. Multiply that by 2, I get like 0.12. And then how good is my data really? Well, again, my first digit of uncertainty is in the 10th place, so I can't argue any better than that. So I take this 0.12 and I essentially truncate it after the 10th place. So I take a look at the next value. Is it 5 or greater? No, it's not. Then I hold it at 0.1. So that ends up being my answer. So again, in that set of data, I had 6 data points, and from that set of data, I gave statistics and say that X bar, the average voltage, is 12.4 volts plus or minus 0.1 volts. That ends up being my answer. So again, you're going to do a calculation similar to this, but again, this concept of the standard deviation is very important. You will use it in other classes, not just physics. Okay. Okay, there's another one I wanted to point out. Yeah. We got that. All right, yeah. So I'm on the bottom of, I guess it's the 3rd page of this document. Any question about what I just got done doing? So we are looking at uncertainties that are after the decimal. What happens if it's before the decimal? What do you do then? So again, this is very, very well written document. I'm going to guess it's probably Professor Benj who wrote it. So let's take a look at another set of data that's kind of toward the bottom of the page. 12,000, so again, this is some sort of volumes. We have 12,360 milliliters. We have 12,449 milliliters. We have 12,201 milliliters. And I'm not going to go through the whole calculation. Right? It'll be the same calculation. 12,298 milliliters. 12,469 milliliters and 12,332 milliliters. Last data is 12,257. Okay, so again, I'm looking at this data table here. It's on the bottom of the, I guess, the third page of the lab. So 12,360, 12,449, 12,201, 12,298, 12,469, 12,332, 12,257. All right. So he calculates the average. I'm not going to go through that. It's the same calculation as we did before. The average, we're going to call this all these values as X1, X2, X3, X4, X5, X6, X7. Going through the same calculation, the author finds that the average, again, you can do this yourself, the average is 12,338. Again, you would add up all the numbers and divide by 7. Get the average, okay? So again, if you did that, there you go. He also finds that the standard deviation, going through the calculation, he finds the standard deviation is 97.4 milliliters. All right, so the standard deviation is a value that's actually greater than 1. It's almost 100. And so when we take a look at all these values, definitely you see 12,000 in all of them. But then the next number, the number in the hundreds place, hundreds, no th, hundreds place, you see variation. 3, 4, 2, 2, 4, 3, 5, 2. So you start seeing that. So that's your first digit of uncertainty is here in the hundreds place. So that really means that my average 12,338, I really don't want to say that. I can't argue this 38, this 38 at the end. I can't argue that. The best I can say is that the average is really going to be 12,300. All right, that's pretty much the best I can do. And what do I normally say? I normally again say that X bar is, I'm sorry. I say that I want to calculate X bar plus or minus 2 sigma. That's really that's really my average, right? So I would say, well, what's 2 sigma? Well, 2 times sigma. So I take 2 times 97.4. 2 times sigma, let me calculate that. 97.4 times 2, 194.8. Now, again, where's my uncertainty? Remember, my uncertainty is in the hundreds place. All right, so basically my 2 sigma, the best I can say is 200. Because that's where my uncertainty is. My first digit of uncertainty is in the hundreds place. Right, hundreds place, right? So I would really say that it's plus or minus. Again, it's 2 sigma, so it's going to be plus or minus. Yeah, 200 milliliters. Right, that's my 2 sigma. That's as good as my data gets. All right, and so Now, what if, for instance, all right, so again, this is the mathematics is the same whether you're below the decimal point or above. So I'm really trying to point that out. Now, his next example is very interesting. You're going to see this concept of this underscore being used if you have zeros, all right? So I think this is an important one to kind of go over as well. Any question about this? Again, this is something you can take to the bank with you in any science class you ever take. So again, this is what's important about this. I'm on, and I wish the pages were numbered, but here we go from the front of the lab. I'm 1, 2, 3. I'm on the 4th page. Top of the 4th page, I see another set of data. All right, now this is very interesting. This is a little bit different. Is I'm measuring some masses. 122.42 grams. Another mass, 120.98 grams. 121.08 grams. 118.51 grams. 119.11 grams. And 118.97 grams. All right, so let me double check that. 122.42, 120.98, 121.08, 118.51, 119.11, and 118.97. All right, so I go through the same mathematics as before. Same mathematics. I find out that the mean, okay, again, add up all 6 of these values, divide by 6. I find out that the mean is actually going to be 120, is what my calculator says. 120.1783 grams. Well, is that value any good? Well, the question is, well, where do I start seeing variability? Well, all of these values begin with a number in the hundreds place. That's a 1. No problem there. But I start seeing variabilities in the tens place. 2, 2, 2, but I get 1, 1, 1. So again, the best I can do, my first digit of uncertainty is in the tens. Well, that's not very good. So, well, if I add, so what that basically tells me is like, well, how good can I really be? Well, if I'm in a tens place, the best I can really say for my average is it's 120, no decimals. It's 120. So X bar is 120. And the zeros, again, the reality is, it's there's really only 2 sig figs. This 0 is really more of a placeholder in this case. Again, it's one of those cases where I have this 0 that ends, like in that case of 1300 I told you about, right? Is this 0 significant or not? From face value, you don't know. This answer could have 2 sig figs or 3. In this particular case, we know that it only has 2. This value really more or less acts as a placeholder. All right, so this value is 2 sig figs. All right, now if I were to go off and calculate the standard, well, essentially, if I were to look at the let's see here, did he calculate the standard deviation? Probably doesn't really matter. One of the things, though, that you can also convince yourself is you can probably better. So this would be grams, but you could write this you could write this also in scientific notation. 1.2, and again 1.2 times 10 to the second grams as well. Now this is where you get into this is where you kind of get into a little bit of a weird situation. What if you actually wanted to express this in terms of milligrams instead? Now again, hopefully you've all seen my chapter 1 lecture by now, but I talk a lot about unit conversions. And again, if you want to go to milligrams, what do you do? Well, X bar, if I have 120 grams Well, what do we know? Well, we know there are 1,000 milligrams in a gram, right? So just like in algebra, the grams would cancel. And what would you have? Well, you'd have 120,000 milligrams. But the question would get to is, well, we have a situation where, again, from the onset, how many sig figs is that? I don't know initially. If I don't know anything else about this problem, I don't know. Do I know it that well? Do I really know it to a million? I mean, to the millionth? Is it really 1, 2, 3, 4, 5, 6 sig figs? How do I be sure in this case? Well, one way to specify, where I have my first least significant figure would be to say, well, where do I have we write it as a least significant figure, we put a little underscore. When you put an underscore there, you are now indicating to the world that your only values that are good are these two values. You really only have 2 sig figs. So again, this is considered a least significant figure. And you put an underscore here. So you'll see that in some of the questions later on in the lab. You'll see this concept of an underscore. Some of you have seen this before, maybe some of you haven't. But this is a situation where, if I see 120,000 milligrams, well, I'm very confused. I don't know if all these zeros are placeholders or if they actually mean something. You must have a really, really good measuring mass meter or something, right? So I don't know what your situation is. So when you put this underscore here, now I know, oh, okay, this really is the only values that I really know for sure. This 0 is not, these are placeholders. So really it's 2 sig figs, just like right here. 2 sig figs is the best I can do. You're not going to get more precision by converting to milligrams, right? I mean, you're still going to have 2 digits of precision, whether you do grams, kilograms, milligrams, picograms. It doesn't really matter. Micrograms, whatever it is that you do, you're still going to have precision of 2 sig figs. All right, that's not going to change. All right, continuing in this lab write-up, again, still on page 4. He talks about the same stuff I talked about before by adding and subtracting, and multiplying numbers of sig figs. I'm not going to talk about that again. And yeah, I'm going to get all the way down to, I'm on the 5th page of the lab now. I believe it's the 5th page. 1, 2, 3, 4. Okay, I'm on the 5th page. Graphical analysis is what he talks about next. And then I think that's probably the last, I'll talk about, it's a little bit more. Graphical analysis, and there's comparisons. I've talked about that a little bit, but I'll officially talk about it. So graphical analysis is very interesting. And again, you're going to see this a lot in Physics 1 and Physics 2. All right. And so sometimes you need to do graphical analysis to make sense out of your data. All right. And so, for instance, he does a great job at talking about this. But let's say we go a little bit later in class, and we talk about forces, chapter 4. One of the kind of forces you're going to talk about is called Hooke's law. And if we don't know what Hooke's law is, I mean, you shouldn't quite yet, but you're going to realize that if you talk about a mass in a spring, if you push a spring or you pull a spring, you displace it from its equilibrium position, the spring's going to push back on you with a force. That force, is given as F equals negative kx. K is called the spring constant of the spring. Now I'm going to forget about this negative sign for the moment and just write F equals kx. I'm just going to worry about the magnitude. This basically says the more you stretch the spring, the more the spring pulls back on you. The more you push the spring, the more it pulls back on you. And this K is like a resiliency factor. Some springs are stronger than others. The spring in your garage door is going to have a very, very large K. A slinky is going to have a very small K. So K is called the spring constant, it's a property of spring. Don't worry about it right now. We're not talking about physics. We're talking about data analysis. All right. So you might think, well, I'm going to, I'm going to measure the force on a spring. I'm going to measure displacement, and I'm going to determine this spring constant K, and it's nothing better than that. And that's my spring constant. Well, there's a problem here with that reasoning, and that is the force has error and the displacement has error. You can have an offset. You can have, your displacement could, for instance, your displacement could have an offset. And what I mean by that is that all the values are off by the same amount, and they're wrong. You think that they're nominal, but in reality, what you're really measuring is possibly the equilibrium value that you think you're measuring plus some delta X that you don't know about. So it may very well be that you have error in here, and so this value is going to be no good, because it's not the equilibrium, it's not the displacement that you think it is. It's, there's some offset. You think it's a displacement, but in reality, it's going to be offset by some error. So how do you get around that? Well, one of the things you can kind of do is say, well, okay, fine. If I'm trying to understand this, actually they wrote it like this. He wrote it like this, but some sort of an offset. Okay, now actually he wrote it like this. All right, so what you're getting is, all of your values are off by some constant amount. Maybe there's something wrong with your experiment, something you're not taking into account. So in reality, what you could say is, well, if I were to, I could say, well, my K is really going to be not X particularly, but X prime minus X naught. All right, and so what I could say is, well, I multiply it, I distribute. It's going to be Kx prime, which is my variable, the actual displacement, minus this Kx naught, which is really a constant. X naught's a constant offset. So really my force that I think I'm getting is always off by some sort of a constant. And I have no idea, that that's happening. So what's one way of figuring this out? Well, I could say the following. I could graph the data. All right. So I could go off and graph the data and say, let's say I look at it and say, well, again, this is kind of like what he says in the let's see, what page am I on right now? 1, 2, 3, 4, 5. I'm on page 6. I see a couple of graphs. Now you look at this data and you see, well, the data looks like it's, it's my force versus X. What should it look like? What do I think it looks like? Well, I think it looks like a linear function. Remember back in algebra, linear is y equals mx plus b, right? Well, I think it's some form like this. So that's a linear function. I think it's a line. It should be a line theoretically, with k being the slope, all right? And so I'll see data that, that has error and it doesn't quite line up. And so I go to, what I can do is I can then go to, let's say, Excel, and I can do what's called a trend line. And Excel will tell you, here's the best fit line. And it'll tell you what it is. It'll say, well, this is Y is some sort of an MX. M is my slope, or MX plus B. B is the slope intercept. Now, when you see this B in the equation, what you know is that B is going to be that B is going to be the offset. All right, so that's the offset. If I did things perfectly, B should be 0. I mean, in a perfect world, my line should actually be coming from the origin going up. But it's not, but it doesn't matter. I have enough data. What I really care about is the slope here. If I take two different points and I say, well, the slope is going to be what? F1 minus F0 divided by two other data points. Changing the vertical over to change the horizontal. I get that slope, M. What is M? Well, that is going to be my spring constant K. So I can literally look at a data analysis. And you can do this in Microsoft. I'll show you as we go in the labs when we need to do it. MS Excel has a very nice way of plotting data points, and you can use what is called a trend line. Again, as I will go through the labs on Thursdays with you, and I'll show you. So for those of you who may not necessarily be so familiar with Excel, there's a nice trend line function where you can actually try to best fit lines to your data, and you can just use Excel to go do that. And so you'll get what that best fit line is. So again, what you can do is, oh, sure, you have an offset, but it doesn't matter. What do you really care about? You really care about the slope. You're after K. So in reality, you're really going to have a y equals mx plus b relationship because your data isn't perfect. But so you don't have to worry about the offset anymore because what you really care about is the slope. Now, how do you see that? You see that through a graphical analysis. Now, what happens on the other hand, again, this is a linear function. F equals kx is a linear function. What happens if you have a function that's, say, quadratic? That's not linear. Let's say, for instance, let's go to chapters 2 and 3 of our textbook. And let's talk about free fall. You drop a ball or something, and you drop it to the ground. How's it going to behave? Well, if I take a look at, if I say, well, here is a cliff or something, and I'll say, and again, as I point out in my lectures, you actually are free to choose a convenient set of axes, and so I can choose an upside down y, for instance. I'm perfectly okay to do that. So I can call this y equals 0 up here, and I can call this some y, and I'll find out in free fall. I mean, I drop a ball and it comes, accelerates to the ground. I'll find out in free fall. Again, I'll find out that y is going to be 1/2 gt squared. G on Earth is 9.80 meters per second squared. That's called the acceleration of gravity. Every planet has its own acceleration of gravity. The moon's like 1.6. Mars is like 3.75, I think. All right. So I'm doing an experiment. And I'm trying to calculate G. Again, we would do this experiment. We're meeting face to face. So what happens? Well, here's the problem. And that is, if I were to look at, let's say, y versus t, well, it's going to look like a parabola. That's not linear. That's a parabola. That's a second order function. But I can make it linear, though. And how do I do that? Well, what I can do is I can do what's called a change of variables. Instead of considering t squared, let's say, for instance, let's consider a variable x, which equals t squared. And so if I do that, I can say I have y equals 1/2 gx. So if I go in my Excel spreadsheet, I can say, well, I don't want to consider times per se. I want to consider times squared. And if I were to graph, say, y versus t squared, or y versus x, what I'll find out is I'll have a line. I'll linearize the function. What is the slope of that line? The slope of that line is 1/2 g. So if I take my data in Excel and I just calculate some sort of a slope, and I want to find out what the gravitational acceleration is, I can solve for it. This is the slope for my data. Okay, I'm in the lab and I'm dropping, marbles through the, this tube, and I have an electronic sensor that's, it's feeding a computer, and it's giving me the time it took to get from one point to another in the tube. That's what you do in the lab. I get that data and I figure out how much time transpired. I put that into my Excel. I square it, and I basically graph y versus t squared. I get a line. The slope. I figure out the slope of that line, and then I say, okay, I want to get a measurement for acceleration of gravity. What do? Well, I'll multiply both sides by 2, and I get that g equals 2m. So whatever my slope is, I multiply by 2, I get a value for the acceleration of gravity. All right. So again, I've taken something that's quadratic in nature and I've linearized it. Instead of saying y versus t, y versus t is going to give me a quadratic. But y versus t squared is going to give me a linear. And all I've really done is made a change of variables. Again, that's something I can do graphically. I can take a look, I can tab my data, do the trend line functionality in Excel, and not a problem. Okay. And as I said earlier, I'm about to complete this. I know most of you guys have gone away. I have 2 of you left, so thank you for that. All right, so at the end, I talked about comparing data with, let's say, a scientifically accepted value, or comparing, let's say, with yourself. How precise are your measurements? All right, so when you're comparing, compare data with a scientifically accepted value. We use what's called a percent error. A percent error. So let's say, for instance, we know the accepted value is A. That's our accepted value, whatever it is. So let's say I'm trying to do this experiment, and let's say that I did that free fall experiment, and I know that the true G, we'll call it G sub A, G accepted, it's going to be 9.80 meters per second squared. I go to my lab. Now, again, I'm just going to say, as an example, I'm going to talk about free fall. All right. So I know, that, the value we use in our book for the acceleration of gravity, how bodies accelerate to the earth, is 9.80. Now, let's say you go to the lab and you do a measured value. Say M, measured value. You go to the lab and let's say you say, well, I would do all my analysis, and I found out that, we'll say G sub M for measured, I found out that I got 10.1 meters per second squared. So I don't have very good instruments, and you'll probably do worse than 10.1 actually. Well, how do I compare with a scientific accepted value? Well, I use what's called a percent error. I say percent error is going to be what? Now, I do a little different than what's written here. I actually always use an absolute value. I take the absolute value of the measured minus the accepted. And I divide it by the scientifically accepted. And I multiply by 100%. That's what I do. I take the difference of what I measured minus the scientific accepted, divided by scientific accepted, and multiply all that by 100% to get a percentage. So what's that going to be in this example? Kind of give you an idea, kind of something to go by. So this example, we'll say percent error is, we'll say absolute value. I mean, I haven't done this calculation yet. So 10.1 meters per second squared minus 9.80 meters per second squared divided by the true 9.80 meters per second squared times all of this times 100%. Now, again, I kind of did some things on purpose here, and that I only know this value, one after the decimal. So again, I might know this, it's 2 after the decimal, but let's kind of see what I get. So I'll do 10.1 minus 9.8, and again, it's already positive, divided by 9.8, and then multiply by 100. And I'll get a percent error. Probably the best I can do, I have 3 sig figs all around, so I could say 3.06 probably. 3.06%. That tells me that is roughly how well I did compared, how well my experiment did compared to the scientifically accepted. I got within about 3% of the error of the actual value. So I can do this when I have, an experiment where I know a scientifically accepted value. Now, you might have a situation where you don't have a scientifically accepted value. For instance, all you really can do is maybe compare 2 different measurements. How well did you agree with yourself? So maybe I did this experiment and I did some experiment and I got 2 values. How close are those 2 values? So a situation where I don't have a scientifically accepted value. Now, you don't always have one. All right. So when you do there, you do what's called a percent difference. So consider a situation where we might not know a scientifically accepted value. So we want to achieve a measure of precision. And report that in our laboratory report. So in that case, I would say consider 2 measurements. M1 and M2. We would then say the percent difference is going to be the absolute value of M1 minus M2 So again, the value is never going to be negative because we have absolute value bars. I'm going to divide it by the average of the 2 values. So I'm going to divide it by adding the 2 values up and dividing by 2. I'm going to take that whole fraction and multiply by 100%. So you would report that as a percent difference. And so in some cases, that's how you report your laboratory. Your laboratory report is either percent error, if you have a scientifically accepted value to go with, or a percent difference. You're really trying to figure out how well do you compare with yourself. How good is your experiment? You report that, you say, well, okay, well, this person, they explain the experiment very carefully to me. I'm the reader, and they got a percent difference of 0.5% or something like that. Okay, well, whatever they're doing, at least their experiment's consistent. If it was a bigger number, I'm like, well, okay, you guys might have a systemic problem. So I don't know how well believe your data. But if the percent difference is very small, then I can have more belief in your data. Okay, that's the theory section. So we're almost done here. So I've gone through 1, 2, 3, 4, 5, 6, 7, 8 pages of this lab. I'm on page 9 of the lab, and essentially it starts off with saying analyzing data laboratory. And all you're going to do there is this is where, so really what do you want to answer so far? Well, everything you should have answered so far is just what's on the first page, your pre-lab page. And then the next place you should start having answers is right here on page, I guess, what is this, 8, 9, hang on. 1, 2, 3, 4, 5, 6, 7, 8. So page 9, 9th page of this lab, analyzing data laboratory. So it'll start off with significant figures. You want to, it's going to give you a whole bunch of different problems of, tell me how many significant figures. Again, you don't have to show your work or anything. You're just basically using logic to determine this. You're going to do some additions and multiplications. And again, you're going to want to give answers that keep in mind significant figures. On the bottom, you have some data. Again, what I want you to do is kind of like what I did. Give me, an X bar plus or minus 2 sigma. X bar plus or minus 2 sigma. Again, the X bar is just finding the average. You use sigma, you do that via the calculation I showed you, the standard deviation. Remember, it's 2 sigma. So what you should have here on the average, you don't just give me the average, you give me X bar plus or minus 2 sigma. So that's what should be written in, so again, I'm on the analyzing data laboratory. I'm on page 9, I guess, if you will. The bottom table says average. You're going to want to give me the average plus or minus 2 sigma. If you just give me the average, I'm going to count it wrong. Is the average plus or minus 2 sigma. Okay, I'm on part B now. Part B is going to give you various, tables. I had somebody ask me a question about velocity. Again, the velocity, well, we haven't covered this yet, and this is a chapter 2 concept, but they give you a formula that tells you what the relationship is between the velocity and the acceleration. All right, so again, this is a kinematics formula. Again, I'm on the top of part B, like for instance, case one, part B. I think I had a question about that. So part B, case 1. Again, this is a chapter 2 concept, kinematics, but the thing to keep in mind here is that you have a velocity is equal to initial velocity, which is a constant, plus acceleration times the time. This is a y equals mx plus b relationship. So this is your y, if you will. I'm just kind of giving you an algebra equivalent. This is a linear relationship. So forget about what the algebra means. Remember the algebra. Y equals, this is your b, this is your m, the acceleration this is your x. So the acceleration is your slope. You're going to find out that the acceleration is the slope of the velocity. So what you're going to do is you're going to essentially graph or look at the velocity versus the time. You'll get some data, get a line. That slope is your acceleration. Now, it's going to possibly not go through 0. It might go, say, at the intercept V0. All right, so your data, whatever your data is, you get a best fit line with a trend line in Excel. Your slope is your acceleration. So your acceleration, again, is the change in the velocity with respect to time. If you use calculus, you find out that that's really dv dt. You use differential calculus. But again, for us right now, the linear relationship is just a change in the velocity over a change in time. That's your acceleration. And so we want to know what V naught is. And so you'll do a trend line. In your trend line in Excel, your Excel trend line is going to look like something like this. All right. It's going to be sum y equals mx plus b. This b that Excel gives you, this is your V naught. Again, you'll use like a trend line in Microsoft Excel. When you find that B is your V naught. And it wants the acceleration, that's your slope. All right, so when you plot the data and you say do trend line in Excel, well, you'll get, you click a little box that show equation, you'll get a y equals mx plus b relationship given to you by Excel. The B is your V naught. The M is your acceleration. All right. So again, these are just, it's a different linear relationship. For case 2, you're basically being given the period of what's called a simple harmonic oscillator. We'll talk about this later on in this chapter as well. And it's basically saying, well, we're going to give you a bunch of masses and periods. Period is t. But the reality is, before I go on, is there any question about case 1 for the 2 of you left here?
It's making sense to me, so I'm okay.
Sarah, are you good with this?
Yeah, I'm good. That helped out a lot. Thank you.
Excellent. I think you may have been the one with the question. I'm not sure. I'm trying to remember. Now, case 2 is linearization. And again, let's not worry about the physics here. We'll cover it in due time. T is a period of oscillation. Well, oscillation means back and forth, like a spring. It's 2 pi square root of the mass divided by the spring constant. Again, I'm not going to talk about the physics, but what we really want to do is we want to essentially we want to plot t squared versus m. Oh, I want to point that out too. When I say plot t squared versus m, what that should mean to you, and this goes back to like the very first page of the lab. I ask you to plot voltage versus current. The first thing you see is your y-axis. The second thing you see is the x-axis. So t squared versus m. If I were to say, I'll just do this for you. If I were to tell you voltage versus current, like in the first page, I think that's what it said in the first page. Voltage versus current. Yeah. Well, what you'd say is, well, what the first thing you read goes on the y-axis. The second thing you read goes on the x-axis, right? So again, this is the lingo. Make sure you get this right, because otherwise your plots are going to be inverted, right? So you see voltage versus current. That means the vertical axis is voltage, the horizontal axis is current. T squared versus m. The first thing is vertical, the second thing is horizontal, all right? Now, if I were to do t versus m, then that looks like a square root. So that's going to look something like this. That's going to be a square root function. But if I say t squared versus m, what does that do? Well, t squared is what? I'm going to square both sides. I get t squared. I square the right side. I get 4 pi squared m over K. I basically have a variable and a variable, and this is my slope. I've linearized the equation. I no longer have a square root form. I now have a line. I've linearized it. This is like a y equals mx, if you will. This is linear. I'm changing variables. I'm not considering t, but t squared. And this is the independent variable m. This ends up forming a slope. So I figure out the slope. The slope is then equal to 4 pi squared over k. And I can solve for k if I want to. I basically change partners here and put k here and the slope down here. So it's 4 pi squared divided by whatever the slope is. I can get a measurement for the spring constant of my spring by linearizing the data like this. So again, this is an example of that, case 2. Okay, part C, we're just computing percent errors and percent differences. And then the end of this is the post lab. In the post lab, I'm going to essentially explain, I want you to explain to me, like post lab question number 1 says, which is more useful in measuring precision of measurements? Percent difference or percent error? Why? And what's more useful, number 2, what's more useful in measuring accuracy? Percent difference or percent error? Why? Okay, I want you to tell me that. And then number 3 is just going to be, student wants to determine the Stefan Boltzmann constant sigma. Student then measures the luminosity, surface area, and temperature of an object. Temperature of the object is changed several times. The student measures the new temperature and luminosity for each of the new cases. Surface area is assumed to be the same as in each case. The data is then plotted to determine the Stefan Boltzmann constant. The student knows the relationship between these quantities given by Stefan Boltzmann law, L equals sigma at to the 4th. How should the data be plotted so that the Stefan Boltzmann constant can be determined? Well, again, what would you do? This is a little bit harder like this. I'll do kind of number 3 for you. I'm going to erase this, and we're pretty much at the end of the lab. So post lab number 3. Some of these labs are written for more university students, university physics students. So post lab 3. I mean, again, a lot of complicated stuff. This is all physics 2 stuff. But what it tells you is that the luminosity, basically the radiant intensity, if you will, is given by a special universal constant sigma called the Stefan Boltzmann constant. It's called the Stefan Boltzmann constant. It's 2 N's, not an M. The area, surface area of the heated object that's radiating. And radiation heat transfer, we'll talk about that in this class. T to the 4th power. And I want to find sigma. This is absolutely not a linear relationship. But what can I do? Well, here's the answer. What you plot, you don't want to plot L versus T. Again, T is a temperature. You want to plot L versus T to the 4th. When you do that, you'll get some sort of a slope. Or you get a straight line. Or you have data, of course, but you get a straight line. You'll find a slope. I'll call it S. Well, that slope's going to be what? Well, the sigma A, if you're plotting L versus T to the 4th, the sigma A is the slope. So your slope is sigma A. So you look at your data and you find the slope S. You want sigma, you divide both sides by A. That's a way of finding the Stefan Boltzmann constant through this luminosity relationship. All right. So where you can show your work, do show your work. If you, again, I prefer that you at least do one standard deviation calculation by hand. But if you want to do the other ones via Excel, that's fine. If you're good at Excel, if you want to do all of them by hand, that's fine. But I at least want to see that you've done at least one of them by hand, because I want to make sure that you've gone through the pain at least once. Because it's very important to understand these concepts. All of this that I talked about tonight, I'm basically pretty close to done. Everything I've talked about tonight applies to all of your science classes. And if you go and become a professional scientist, which is why you're here, it's going to be these are going to be useful tools. In fact, what I would do if I was you is I'd take this lab and I would just put it someplace as a reference for classes that you have in the future, your chemistry classes, because this stuff is not really just physics, it's data analysis. It is good for any of your science classes. Okay, that's pretty much all I have. Do you have any questions? I went through a little bit more than I thought I was going to tonight, so I think I bored most of my students here. Any questions?
I'm good on my end. You went over everything, so thank you. I appreciate that.
Absolutely.
Yeah, same. I agree. I appreciate it very much.
Great. Yeah, so this is like I say, this is Tuesday, so you got 3 more days if you haven't, and there's certain things you haven't figured out yet. I mean, just at least, this is a fairly large data packet, but at least the homework is not too much. I think the first week is only 4 problems, so I guess there's no free lunch in science. Yeah, you get it easy one way, you get it hard the other way, I guess. So, all right, well, I guess I'll call it a done deal if you guys are good.
Yeah, I'm good on my end. Well, thank you.
All right, have a good night.
You have a wonderful night. You as well.
Yeah, thank you. Good night.
Good night.